Bismillah ar-Rahman ar-Rahim. This is a lecture of Physics 110, Physics for the Life Sciences. Today we will study chapter 23, that is the diagnostic ultrasound imaging. In this chapter we will explain how can we use ultrasound wave in diagnosis and to reconstruct the image of different tissue inside our body. The aim of the present chapter are first to understand the use of ultrasound wave in diagnostic. Second, to understand how can we reconstruct the image of different tissue or organ in the body. But first, let's go to some definition of this chapter before going on discussing the chapter itself. Ultrasound. It is a sound wave that have frequencies more than 20 kilohertz. As we know, the human ear can hear frequencies in the range of 16 hertz up to 20,000 hertz. Therefore, the sound that has frequencies more than 20,000 hertz is considered as ultrasound. Interface. It is a layer between two different tissues. For example, if we have two layers, one is fat and the other is muscle, and they are on each other, the layer between them exactly is called interface. Transducer. This is a device that emits ultrasound and detects ultrasound. So it emits and detects ultrasound. Echo. It is the reflection of sound wave. Consider that ultrasound wave is incident on the interface between two boundaries, fat and muscle. This wave will transmit and reflected. The ratio of reflection and the ratio of transmission is given as first the intensity transmission T. It is the ratio of intensity sound transmitted to the total intensity at the interface. And the intensity reflection, it is the ratio of the intensity of sound reflected to the total intensity of sound at the interface. Of course, as we know, in the case of sonar in submarine or bats or dolphins, they all send an ultrasound wave to the surrounding. Then the ultrasound wave reflected back, carrying information about what is in front and around the submarines or bats or dolphins. Here also we use the same idea but using transducer. This is a device that emits ultrasound and detects ultrasound also. However, in the present work of diagnostic and imaging of ultrasound, the wave is incident and enters to the body, then some reflects from the tissue we want to study, and some transmitted inside this organ or this tissue. According to the value of reflection and transmission, we can get some information about the organ or about the tissue. And the ultrasonic imaging, it generates a sound that travels through the skin into the tissue. Then it reflects at various interface, and it detected as an echo, then return back to the transducer. Now let's go to the next part, that is the relative intensity of waves. As we mentioned, consider that there is a flat interface between different media. For example, the flat interface between fats and muscle. At the interface, the incident wave is partially reflected and partially transmitted. According, according to this, and in order to satisfy the continuity of the physical properties across the interface, there are two important conditions should be verified. The first is the speed should be additive quantity. The speed of the incident reflected and transmitted should be additive quantity. Second, the energy at the interface should be conserved. So these are the two conditions. First, the transmitted speed of the wave, that is Vt, should equal to the sum of the incident Vi and the reflected speed Vr of the wave. This means that Vi plus Vr should equal to Vt. Second, the energy passing through the interface should be conserved. This means that the reflected plus transmitted should equal to 1. R plus T should equal to 1. At the interface, an incident wave is partially reflected and partially transmitted. Therefore, the relation between the transmitted speed and the incident speed is Vt is proportional directly to Vi. As Vt increases, Vi increases. And the proportionality constant is 2 rho 1 C1 divided by rho 1 C1 plus rho 2 C2, where rho is the density of the material or the medium, and C is the speed of sound in the medium. This means that it depends on the medium. So the proportionality constant here depends on the medium. Therefore, we can get very important parameter here that is called acoustic impedance, where the acoustic impedance is defined as the multiplication of the density multiplied by the speed of sound in the medium. It depends mainly on the medium. Therefore, we can write this equation Vt equal to 2Z1 divided by Z1 plus Z2 Vi, where Z1 is the acoustic impedance of the first medium, Z2 is the acoustic impedance of the second medium. The units of the acoustic impedance, of course, we know that the Z equal to rho multiplied C. Rho has units of kilogram per meter cubed and C has units of meter per second. Therefore, by multiplying them, we can get the units of acoustic impedance as kilogram meter to the power minus 2, second to the power minus 1. This is called real. To produce an ultrasound scan, we need many reflected ray interaction, many reflected intensity, and many transmitted intensity in order to get the or many two-dimensional image. So to produce the ultrasonic scan, we need reflection from several boundaries within the body. This required some of the ultrasound to be reflected and some to be transmitted. The transmitted should be reflected again and transmitted again and so on. Of course, by using the property that is the acoustic impedance, this allows us to calculate the intensity reflection and intensity transmission and compare between them. The next we need to discuss is what happens when the wave meets a boundary. You already familiar with reflection law as it was discussed in chapter 21. Actually, we here we here not only interested in the refraction part, but also to what happens to all the wave as it passes through the interface. In fact, when the wave incident to the interface between two boundaries, some waves reflected and some waves transmitted. The reflected part is the intensity reflection, R equal to reflected intensity divided by the total intensity, and intensity transmission, T equal to transmitted intensity divided by the total intensity. According to the conditions that we have mentioned before, especially the second condition that states that the energy should be conserved, therefore we can say that R, the intensity reflection, plus T, the intensity transmission should equal to 1. The equations of the intensity reflection and the intensity transmission can be given from these two equations. R equals Z2 minus Z1 divided by Z2 plus Z1 all square. T equal 4Z1 multiplied by Z2 divided by Z1 plus Z2 square. In order to understand what happens here, we will go to discuss this example. Here, we use an ultrasound signal with frequency f equal to 2 megahertz. This is, of course, ultrasound signal. And an incident intensity of I equal 5 multiplied by 10 to the power minus 2 joule divided by joule per second per centimeter square. Of course, we know that joule per second is what? And in order to convert it, it becomes 50 milliwatt per centimeter square. How much intensity does the signal lose before it reaches the fat muscle interface? Of course, here we have to get the value of the acoustic impedance Z1 and the acoustic impedance Z2 of the first and second boundary, as it given here in this example. In order to get the intensity reflection and intensity transmission, we use the above mentioned equations. So we can get here the intensity reflection is about 0.012, that is 1.2% from the whole intensity. And of course, the intensity transmission can be given as 98.8% from the whole incident radiation. From here, we can distinguish between this transmit the intensity of reflection and intensity transmission, and we can get some information. Of course, this means that only 0.6 milliwatt per centimeter square is reflected from the whole radiation, and 49.4 milliwatt per centimeter square transmitted. Now let's go to the next part, that is ultrasound imaging. Here we will simulate an actual ultrasound imaging application. As we can see in this figure, the ultrasound frequency is emitted from the transducer and then it detected it. At the interface, we use fat-like fluid of acoustic impedance is very close to the acoustic impedance of fat. And of course, Z1 is the acoustic impedance of the first layer, and Z2 is the acoustic impedance of the second layer. We want here to explore the various properties of the ultrasound echo that we received from the fat muscle interface. Therefore, we use two very important parameters that's called the sound absorption and the echo delay time to reconstruct the three-dimensional image from the many two-dimensional images. Actually, these two values, the sound absorption and the echo delay time, using with some mathematical formulas, are very important to put limits to what we are going to see in the image. Okay, so this is the end of chapter 23, and thank you very much.